Hi everyone, today I will talk about wavelet transformation. The first question you may have is what is wavelet? Basically, it is a short piece of wave as drawn here. And to be more technically, it is a rapidly decaying wave. And it's equivalent to a oscillation with zero mean. Let's say if we draw an axis horizontal y equals to 0 here, then the area above this axis should equal to the areas below this axis. And this is in contrast with the sine waves that we usually see in the Fourier transformation case, because sine waves extend to infinity, while this wavelet has finite duration. Then let's compare the Fourier transformation with the new introduced wavelet transformations. We know that in the Fourier transformations, we tend to represent the signals as the sum of a bunch of sine waves. And this differs in wavelet transformation as we approximate the original signal using the wavelets. If we look at the formula of Fourier transformations, we know that it is the integral of the original signal multiplied e to the negative j by ft. For the wavelet, it differs only in that it will multiply the phi ab t, which means that they only differs in the analyzing functions part. This means that in the Fourier transformation, we only focus on the frequency components, but in the wavelet transformation, we focus on the scale and the translation components indicated by A and B. This means that the coefficients in the Fourier transformation will correspond to the frequency components only, but in the wavelet, it will correspond to both the scale and the translation components. Then, why we need to use the wavelet transformation? What will be its benefit over the Fourier transformation? If we plot the time resolution versus frequency resolution in a 2D manner, we can see is that in the wavelet transformation case, we have the both time domain information and the frequency domain information, and high scale means low frequency, which corresponding to a bad time resolution, and low scale means a good time resolution but a bad frequency resolution. However, if we plot similarly for the Fourier transformation, we can see that there is zero time resolution. All we have is the frequency components. So we lose the information from time domain, but for the wavelet transformation, we can get both, and that's the benefit. Then we would explain in details what will be the scale and translation previously mentioned. For scale, it means stretch or compress the wavelet. Let's say we are given a wavelet of a certain center frequency, and by scale it by 2 means that we actually stretch it, make it slower, and for the scale by a half, it means we compress it, making it faster. And that's the scale. For the translation, it is straightforward because what it means is basically we move the original wavelet along the time axis. So that's basically what it means by translations. What we need to notice is that for the scale case, low scales means that the wavelet can catch the abrupt change, and high scale means that the wavelet can catch the slow change. Next, we will explore the application of the wavelet transformations in the nano imaging, taking the discrete wavelet transformation as examples. Discrete wavelet transformation is equivalent to compare a signal with discrete multirate filter banks. Let's say we give an original signal and its spectrum is shown in the frequency domain. What we did when we apply the discrete wavelet transformation is that we split it into a low-pass filter portion and a high-pass filter portion, and we discuss the unwanted portion, and for the remaining portion, we apply the same splitting method and keep doing this until we get what we want. And this is good because there is very few coefficients left, so this makes it ideal for denoising and compression purpose. It also has interesting applications in the AFM imaging techniques. Here we have basically an AFM model which consists of photodiode, a laser, and a cantilever. And we have the sample here, we have the control loops. Inside the control loops, we need to do the data acquisition and the image processing. So what's the problems? The problem is that for the conventional AFMs, it usually requires locking amplifiers. And these locking amplifiers has a finite bandwidth, and this makes it not ideal for the high-speed application scenarios because it lost some of the transient response and it only catches the steady state response well. Then how will the waveless transformation help the AFM? Basically, let's say in the data acquisition and the image processing part, instead of the conventional ways, we started from the original get real-time deflection signals, and we apply the XWT to get its phase map, while at the same time to use CWT to get its amplitude scalograms. Then what we get is the phase signal and the amplitude signal in the time domain. So we have time domain informations. And then we can reconstruct the phase images and amplitude images. This will help us overcome the limitation of the locking amplifier because we now do get the transient response instead of steady state only response. So that's basically the benefit of waveless transformation in AFM. And that's all about the video. I hope you enjoyed it.